to invite Gert Laursen from the Odense, from the Odense city in Denmark. Gert is the second time he's presenting in this university. Thank you very much for coming twice. And I didn't forget that I promised you an excursion in the Danube Delta. I was not able to organize it again, but next time I for sure I'm going.
You always promise.
Right.
Thank you very much. Unfortunately, I haven't had the luck of visiting all these exotic places as Rolf were telling us about before, but I have more than 30 years of experience in the state of Denmark in very different authorities, different counties, private consulting companies, and for the last 10 years as I call it hydro generalist in the municipality of Odense, dealing with all sorts of hydrochemistry, hydrogeological, groundwater related issues. To those of you who are not familiar with Denmark, I found this funny projection, Google projection. In real life, Romania is actually more than 6 times bigger than Denmark, but this is the whole of Denmark. We have more than 40,000 kilometers of coastline. No, 40,000 square kilometers, 7,000 kilometers of coastline, and in the middle we have Funen, and in the middle of Funen we have Odense, and there's a little municipality of Odense here. As a geologist in a municipality, of course, we produce a lot of data. But when it comes to real data, I think we are more end users, and we've been mentioned as such several times. But as an end user, I want to raise a claim, some sort of claim. Of course, we have tons and tons of very fine data, with databases, time series models, reports, and so on. But my claim is that very often we don't know the data exists. We simply forgot to use them. We have heard lots of examples today. Maybe we know the data exists, but we can't find them. Maybe when they become relevant, or they will become expensive or too time-consuming to get to work. Or data are not transformed into knowledge and decision-supporting tools. Or something else, or more important, happens when we have to deal with these data. An example could be extreme, and therefore a very good example. Here we have Mexico City. Almost 500 years ago, the Aztec capital were smashed and dozed into a lake, and a new capital were made on top of it. And it turned out that the dried out lake wasn't the best foundation for building constructions. Dewatering, oxidation, subsidence, and so on, they are all well-known impacts. But nevertheless, central parts of Mexico City, I think maybe it's world record subsidence or subsidence 40 centimeters per year. That's quite a lot. There are very few unknowns, at least I think. We have lots of data. Lots of data are turned into knowledge, decision-supporting tools, but at the end, something are more important apparently than dealing with these sorts of problems. Another example from where I come from, buried and abandoned city gate. Here we have the main rail system in Denmark. Here we have Copenhagen, our capital. Here we have our next city, city Aarhus, and this is the main rail system. Last summer, the Danish Rail had to do some comprehensive maintenance of their rail beds and underlying drainage system. And of course they did it in the summer holiday because the pendlers were not much at that time. And of course the guys in the Danish Rail, at the Danish Rail, and their contractors aren't stupid, deranged or absent-minded. And they made a very detailed planning of the maintenance of the rail bed and the underlying drainage system. And they looked after all sorts of subterranean infrastructure, but they simply forgot to look for buried, abandoned city gates. And that's the unknown unknowns. They simply didn't know that they should look for these sorts of structures. Actually, some of my colleagues were leaning back and say, why the heck didn't they ask us? But these guys were not aware that their knowledge were looked for. So these two things were not brought together. And the result of this, when all this big maintenance machinery came here, they just had a really problem. And the result of that was that 75% of all traffic, all train traffic, passenger traffic, and all freight trains from the northern part of Scandinavia going this way over here and to the rest of Europe were cancelled for almost a week. That's expensive. Another example when it comes to above below ground in a municipality sort of way, we have two very different worlds that meet, the above and the below world. And of course it's not necessarily opposite objects, but it's very different objects. Of course the above below issue, urban suburban, data versus politics, the geospecialists versus the planners, and different laws. The Planning Act, we have a very good Planning Act, but it stops at the surface, and below we have very bad legislation. Also 250 meters below, then we have the underground law, and then the states take over, then everything is controlled again. So I think very often we fail to account for time. We have discussed it, seen lots of examples, and we forget to do this 3D dynamic spatial planning thing. And I want to show you an example. Just very short information about the municipality. 300 square kilometers, 175,000 inhabitants within the city limit, 200,000 inhabitants at all in total. Mind this characteristic border now. When we do a little data digging, one way of one sort of data could be old maps. We have lots of these in the archives. Odense is one of the oldest cities in Denmark and very well described. I would like to show you very brief the evolution of Odense, starting here, 1580. And mind this green spot, and this is about 30 football fields and a population of 4,000 people. time passes by, almost 300 years ago. This is the time when Hans Christian Andersen lived here, and actually 1853 Odense was the first city in Denmark to have their own waterwork. It started in 1953, and the same year 7,000 people died in Copenhagen due to cholera. Time goes on. And that's the situation of today. There's almost 100 square kilometers of city. About 1/3 of the municipality is covered by city. If we take all these maps, digitize them, calculate their size, their square kilometers, and we can put them here in this a logarithmic scale and in acres, and here we have the time series. We get from 1830 and until today, we get a straight line, and that's a straight line on a semi-logarithmic paper equals exponential growth. And some clever people say that one of mankind's biggest problem is that we don't understand exponential growth or the consequences of it. I have found out today that actually we grew much more than Oslo. We grew 3.2% per year. Is that good or is it bad? Our mayor is happy, but it actually means that we have a doubling time of 22 years, meaning that around 2045, I think, the city of Odense will not fit in the municipality of Odense. I don't know if it's a problem, but it's a good way of thinking, and we have taken some consequences of that, and we have decided to doing lots of city densification. 30% of all new buildings have to be done within the city limit today. The city growth was a fact. Here I have an example of another fact. Mean annual precipitation for the last, we started measuring 140 years ago. Mean annual precipitation have gone up with around 100 millimeters. That's quite a lot. And we have to deal with these extra amounts of water. A third fact. If you remember the maps from before, we saw the rapid growth of city size occurred in around the 1930. And here you see the water abstraction, as this is the total amount of water being abstracted in Odense. This red is abstracted outside Odense. This yellow is abstracted inside, and this is not that straight, but it continues growing. And here, around the 1900, we are 40,000 inhabitants, and today we are 200,000. And we see lots of interesting characteristics. We have this massive water abstraction that starts here inside Odense, and it's due to deterioration of water quality, pesticides, and the waste from the waterwork they would abstract somewhere else. And the total abstraction here reaches about 18 million cubic meters per year. And green taxes started the water prices went sky high, and that people started saving water. And the result is that today we use about half the amount of money. But we have the inhabitants, the number of people inside the city have kept on growing. We have showed, like I showed before, we have seen lots of examples of city growth, water abstraction that can be a dangerous cocktail due to heavy subsidence, for instance. But what happens when the abstraction stops, maybe being minimized, or maybe even stops? I can show you an example from here. The green spot I showed you before has turned yellow now, but it's this position in 1870. Here is the map of the 1870 situation in the southwestern part of Odense. The waterwork is here, and this is the situation today. And I will show you the pitchometric head measured in this point. That's a copy from around 1930 and until today. The abstraction starts here. You see the ground surface. And the problem is that in this period, the groundwater level, pitchometric head, is going from around plus 11 meters above sea level to minus 2 meters below. And in this same period, the urbanization takes place because it was former peat excavation area, and everything turns out becoming dry and very easy to urbanize. And at the end, the abstraction was reduced due to water quality problems and other things, and here the complaining starts. That's the reason. You start. This is not rainwater derived. Actually, it's from below. So of course, people are not satisfied with this results. But it's a fact of life when we make these sorts of handling problems. Another example, here we see northern part of the city, all these red dots showing places where a mixture of sewage water and rainwater have been on the floor in the basements of the buildings. These are showing places where there actually have been flooding above terrain. So of course there is a problem. The reason why is very easy to explain. Here we see the same area in the 18th century. We have all these old wetlands, peat excavation places, and if we put on top some situation as we see it today, we know the story. If we remove the houses and just look at the terrain model, we have these three different problems. The upper part of the old river is put into the pipe system. Here we have still open system, and this old system here is abandoned and not functioning anymore. So of course we will have problems. So we have three facts. We have abstraction is going down, especially within the city. We have the use of water is more than half, as I showed you before, and we have mean annual precipitation is going up. Here we have a model showing what to expect if we reduce the abstraction to the amount of water being abstracted in the year 1900. So this is here we will have lakes. So that's okay. But shall we start worrying or shall we start whining? I don't know. Actually, I think we understand what's going on, not in detail, of course, but we of course we shall stop whining. And there are much we can do about it. And some of the thing I think we could do is we have a very detailed three-dimensional geological model, and Ms. Peter will come back to this later. But on top of these, I just want to we have this pipe system, all buried infrastructural things we have modeled. We have the ditches, the trenches modeled, and we can fill it all with our knowledge about geology, man-made ground, and everything. But on top of this, we have to supply it with archaeology, pollution stuff, our knowledge about surface near groundwater issues, where we have good recharge possibilities, where we have the well fields, the basements, we have parking lots in different levels, and these buried city gates I told you about. And on top of this, we can put not a BIM, but a SIM model, and then we can start visualize shallow, deep groundwater tables. We can see where we have these French drain sods and everything. We can visualize the protection or abstraction zone for potable water, hot zones if we want to make some energy storage. And when we have this fully three-dimensional model, and it's not just another advanced 3D model. This is my humble wish. We haven't got it today, but we need a functional tool that within a city model, with a city model on top, in an easy and intuitive way, can handle, combine, and most importantly, visualize all sorts of these underground informations, from basic geology, geotechnical things, archaeological things, aquifer, specific water levels, protection, abstraction zones, zones for potable water, hot zones, and so on, to all sorts of buried subterranean infrastructure. I think this is a main tool for us as geotechnicians, some sort of specialists or hydrogeneralists, to address all these issues for our planners and for our politicians. We haven't got the time to read and to write all these reports and database things, and they haven't got the time to read it, but everyone have the time to look on clever visualized things. And at the end, I will just 1 minute for a little bit of worrying. I want to make a little commercial concerning these. The European Environmental Agency reports concerning precautionary principles and discussing what they call late lessons from early warnings. All these sorts of aspects have been discussed in these reports, discussing why most of these catastrophes occurred, and that's really fascinating readings. Actually, the specialists are telling us that our way of dealing with nanomaterials today very much resembles the way we dealt with asbestos around 1910. In 1910, not everybody, but lots of people knew asbestos is really not a good thing. But we had to pass 100 years more before we actually took the step to get rid of it, to abandon it in our way of working. My little claim could be if we continue to accept the way that water is drowning part of our cities today, maybe we will, maybe our ancestors in 50 years will say and wondering what the hell were they thinking about, because my claim could be that in parts of Odense the indoor climate will deteriorate in a way that we haven't seen coming, and it's that's just one of the frog stories that we were discussing yesterday. The slow cooked frog hasn't got a chance because it doesn't see it, but I think we will experience a lot of severe indoor climate within the next 10 or 20 years. Thank you.
Yes.
And how are you going to solve this groundwater flooding in the basements?
Actually, we can say that it's the same as people have to protect themselves against flooding from the sea. It's their own task to do it. But we can help them. For instance, we cannot, but our water supply, the water company can turn up their pumps again, but they have not. It's bad
Because in Holland also they tell us this is your problem. You must solve your private groundwater situation in your house.
Yeah.
But for example in Delft, there's a long discussion there. You have a huge factory pumping also 15 million cube a year, and they want to stop because of the taxes. And then they were telling the government, don't stop, because it's the same as you. That was already 100 years. So they constructed all neighborhoods with a low groundwater level, and even we believe that subsided also. And now they were so now this they were paying. The government was paying the taxes for the company that they won't stop with pumping.
Actually, I think we have a moral problem, because even if it's a private waterwork, it's 100% municipality owned.
Yeah.
But waterworks, our legislation says that when you are lowering groundwater and the damage being done in that connection, you have to pay. But when you stop pumping and the water returns to normal, if you have remembered to warn your neighbors and everything, you're not supposed to pay anything of these.
Yeah.
Thank you very much. We are going to